Hi students, in the last video we discussed about different types of probability density functions and distribution functions. Out of different types, we discussed two types of distribution and density functions for discrete random variable. So now I am going to discuss about the remaining three density and distribution functions for a continuous random variable. The three are uniform density function and exponential density function, Rayleigh density function. So let us take one by one. The first one is uniform density function. So now for any random variable x, the uniform density function is given by fx of x is equal to 1 by b minus a for the given condition a less than or equal to x less than or equal to b and 0 for other values. So this is the given uniform density function, and here a and b are constant values, and the values of a and b always lies in between plus infinity minus infinity, and b is always greater than a. So now I have uniform density function of x of x, and now to get a uniform distribution function. Uniform distribution function. So uniform distribution function and uniform density function are related by this property of distribution and density function, that is here generally fx of x is equal to minus infinity to x fx of x dx. This is the relation between distribution function and density function, but the uniform density function fx of x lies between a to b, and it is starting from a. The starting limit is a only, so that's why you can write this as fx of x is equal to integral a to x fx of x dx. So now I can write here a to x, the given function is 1 by b minus a dx. So you can integrate the terms. 1 by b minus a is a constant, and then you can write here this as b minus a integral a to x dx. So it is going to be 1 by b minus a, what is this, x only, and the limits are xa. So now I am just substituting the limits, so then you can get x minus a by b minus a. So this is the generalized expression for uniform distribution function. Now I am taking the conditions. If the limit x is equal to a, what happens? If the limit x is equal to b, what happens? Because the density function is given, the given density function is lies between a and b only. So for the given limits, what about the distribution function? That is, we need to verify. So now the limits, if I am taking limit x is equal to a, so then the distribution function fx of x from this expression, if I am substituting x is equal to a, if I am substituting x is equal to a, so then what happens? Here I am substituting x is equal to a, so a minus a by b minus a. So this is going to be 0. Now I am taking x is equal to b, the other limit. So x is equal to b means the given function. So here you can write a, so fx of b. So what happens here? B, x is equal to b minus a by b minus a. So the two gets cancelled and the value is 1 only. Okay, for the given conditions a and b. So finally, I'm going to give the distribution function for the given limits as per the density function. So here you can take 0 for x less than or equal to a, and here the expression is x minus a by b minus a for a less than or equal to x less than or equal to b. If x is taken as greater than or equal to b, you can take this as only less than, and here this is also less than only. A less than x less than b, you can take this expression, and if x greater than or equal to b, the value is 1, because if you substitute x is equal to b, then you are getting 1 as the answer. So if x is equal to a, you are getting 0. So if for x is equal to a, the function is becoming 0, means there is no function validity for less than a. So that's why I'm taking the 0 value, and for x greater than b, the value is 1. And in between a and b, you are getting this values of distribution function based on this expression on x minus a by b minus a. So this is the final expression with respect to conditions for the distribution function. So based on this, I can draw the graph here. So a graphical representation for this. So now I'm taking density function. So what is the density function? It is going to have 1 by b minus a in between a and b. So it is a constant value. So here I am taking the value as a constant value at this point. So 1 by b minus a, and it is going to be constant. It is going to be constant from a to b. There is no any change. So it is going to be a constant value. Okay. So now I am taking distribution function representation also. Fx of x. So what is the value based on this function? So you can take the graph here. You can see this value for x up to x is equal to a, the value is 0. So now I am taking up to x is equal to a, I am taking a, so the value is 0, and at the b value, the value is 1. So here I am taking b, the value is 1. So I'm just taking this as 1. So x greater than or equal to b, the value of the function fx of x is 1. So from a, it is a function. So you can write this as, you can draw this as so this is the graphical representation for density function. That means here the uniform probability density function has a constant amplitude in the given range a to b. Okay, and the total area of the function is always 1. Okay, and when you go for the applications of this uniform density function, generally this uniform density function or uniform distribution function is always used in round of conditions. So round of condition means if I have some values, take a real number into an integer, so we need to take the error value same for all the values. Okay, so we need to distribute the same error for all the values, then you can normalize the values. Okay, so this is about uniform density function, and we can go for exponential probability density function or exponential. probability density function. Exponential probability density function. So this is one of the important density function in the examination point of view. So now I am taking a random variable x, a defined random variable x, and the corresponding exponential probability density function fx of x is given by 1 by b e power minus x minus a divided by b for x greater than or equal to a, and 0 for x less than a. So this is the density function. Again, we'll follow the same procedure as in the case of uniform density function to derive the distribution function fx of x. So based on the property of density function, I can write this fx of x is equal to minus infinity to x fx of x dx. But the limit for this given density function is from a only, so that's why I am taking the lower limit as a to x fx of x dx. Okay, so now you can substitute fx of x as per the definition of the exponential density function a to x. So this is given by 1 by b e power minus x minus a divided by b dx. Okay, and now you can integrate the term e power minus x minus a by b, then you can get minus 1 by b into e power minus x minus a by b, and you can substitute the limits x a. So then by substituting the limits, you can get fx of x is equal to 1 minus e power minus x minus a by b. Okay, so this is the expression for distribution function. And again, you can take the limits x is equal to a in the condition, then you can get the final distribution function for different conditions. So as in the case of uniform density function, you can substitute the values, so then you can get 0 for x less than or equal to a. Okay, take same value x is equal to a here, so then what happens, a minus a 0 e power 0 means it is going to be 1 minus 1, it is going to be 0. So if x is equal to a or for x less than a, the distribution function is going to be 0. So you can take the value as 0, and if you take x is equal to infinity, here x is equal to infinity, then the term e power minus infinity is going to be 0, and the value of distribution function is always 1. So here you can take 1 for x is equal to infinity, and for other values, that is x less greater than a and less than infinity, then you can get this expression as 1 minus e power minus of x minus a by b. So this is the final expression of distribution function for the given conditions. And you can also represent the density and distribution function here with respect to graphs. A very simple graph I am going to draw here. So now I am taking density function. So density function is given by 1 by b e power minus x minus a by b. So for x less than a, the value is 0. So you can get from x is equal to a, the value is 0. And the maximum value is going to be 1 by b only, because 1 by b into e power. So that's why you can take 1 by b is the maximum value. So then I can take this as so like this, and the term is exponentially reducing because e power minus x, so the term is going to reduce exponentially. So now we can take 1 by b e power minus x minus a by b here, so it is going to reduce like this. So this is exponential density function. So now I am drawing exponential distribution function. So again, as per the given conditions, the maximum value is 1 and minimum value is 0 from x is equal to a. So it is starting like this, and slowly it reaches to 1 at infinity. So as per the given conditions. Okay, so this is about exponential probability density function and distribution function. And here the exponential probability density function is having maximum value of 1 by b at x is equal to a, and exponentially decreases to 0 as x is increasing, that is x is equal to infinity. Okay, and if you take the applications of this exponential function, the distribution of raindrop sizes. Raindrop sizes. The distribution of raindrop sizes is possible to measure using this exponential distribution functions, and the distribution of fluctuations in the signal strength. Signal fluctuation strength received by the radar receivers also possible to measure using this exponential density function and exponential distribution functions. Okay, so this is about the two density and distribution functions. Thank you.